Welcome to our section on Introduction to Correlation Analysis. Correlation analysis is a powerful tool in statistics. It helps us understand the relationship between two variables. We can see if they move together or in opposite directions. This is valuable in many fields. We use it in finance, healthcare, and social sciences, among others. The basic idea is simple. We look for patterns in data. Do high values of one variable tend to occur with high values of another, or do they occur with low values? Answering these questions helps us understand how variables are connected. Correlation does not tell us about cause and effect. It simply reveals if a relationship exists. This information is crucial for making informed decisions. We can then investigate further to uncover potential causal links. Understanding correlation is fundamental to data literacy. It empowers us to see patterns and make sense of the world around us. This knowledge is essential for navigating our data-driven society. Now let's dive into Section 2, Correlation versus Causation, Understanding the Difference. Correlation and causation are often confused. It's crucial to distinguish between the two. Correlation means two variables change together. Causation implies that one variable directly influences the other. Let's illustrate with an example. Suppose we observe a correlation between ice cream sales and crime rates. Both tend to increase during summer. This doesn't mean ice cream causes crime. The hidden factor here is temperature. As temperatures rise, people crave ice cream, and more people are out and about, increasing the opportunity for crime. This example demonstrates that correlation doesn't equal causation. It's tempting to draw conclusions based on correlation alone. However, doing so can lead to flawed assumptions. Always remember, correlation is a clue, not a conclusion. It suggests a potential relationship that requires further investigation. Moving on to Section 3, Types of Relationships and Scatter Plots. Correlation analysis reveals different types of relationships between variables. These relationships can be positive, negative, or non-existent. A scatter plot is a useful tool to visualize these relationships. In a positive correlation, both variables move in the same direction. As one increases, the other increases as well. For example, height and weight often have a positive correlation. Conversely, a negative correlation means variables move in opposite directions. As one increases, the other decreases. An example is the relationship between exercise and stress levels. Lastly, no correlation implies the absence of a consistent relationship. Variables fluctuate independently of each other. For example, shoe size and IQ have no correlation. Understanding these types of relationships, visualized through scatter plots, is fundamental to interpreting correlation analysis. Section 4, Correlation Coefficients, Measuring the Strength. While scatter plots visualize relationships, correlation coefficients quantify the strength and direction of the association between two variables. These coefficients range from -1 to +1. A coefficient of +1 indicates a perfect positive correlation. This means that as one variable increases, the other increases proportionally. A coefficient of -1 signifies a perfect negative correlation. As one variable increases, the other decreases proportionally. A coefficient of 0 suggests no linear relationship between the variables. They are not correlated. Values between -1 and +1 represent varying strengths of correlation. The closer the coefficient is to -1 or +1, the stronger the relationship. Conversely, a coefficient closer to 0 indicates a weaker relationship. Correlation coefficients provide a standardized way to compare and interpret the strength of relationships between variables. They are essential for drawing meaningful conclusions from correlation analysis. Section 5, Pearson, Spearman, and Kramer's V applications in different data types. Different correlation coefficients are used depending on the type of data being analyzed. Three commonly used coefficients are Pearson, Spearman, and Kramer's V. The Pearson correlation coefficient is used for linear relationships between continuous variables. Continuous variables are those that can take on any value within a given range, like height or temperature. Spearman's rank correlation coefficient is used for monotonic relationships between variables. A monotonic relationship means the variables tend to move in the same direction, but not necessarily at a constant rate. This coefficient is suitable for ordinal data, where values have a rank but not a specific numerical difference, like rankings in a competition. Cramer's V is used to measure the association between two categorical variables. Categorical variables represent groups or categories, like gender or eye color. It is particularly useful when analyzing data in contingency tables. Choosing the appropriate correlation coefficient ensures accurate measurement and interpretation of the relationship between variables. This choice depends on the nature of the data and the research question. Section 6. Correlation in Prediction Analysis. Correlation analysis is a cornerstone of prediction analysis. By understanding how variables are correlated, we can make informed predictions about future outcomes. For example, if we know there's a strong positive correlation between advertising spending and sales, we can predict future sales based on projected advertising budgets. Similarly, understanding correlations in weather patterns helps meteorologists forecast future weather conditions. However, it's crucial to remember that correlation does not guarantee accurate predictions. While it provides valuable insights, other factors can influence outcomes. Therefore, prediction models often incorporate multiple variables and sophisticated algorithms to improve accuracy. Nonetheless, correlation remains a fundamental building block in the field of prediction analysis. Section 7. Conclusion: Correlation analysis in the bigger picture. Correlation analysis is a powerful tool for understanding relationships between variables. It helps us make sense of complex data and uncover hidden patterns. While correlation does not imply causation, it provides valuable clues for further investigation. From identifying trends in financial markets to predicting disease outbreaks, correlation analysis plays a vital role in various fields. It empowers us to make informed decisions, develop effective strategies, and advance our understanding of the world around us. As we navigate an increasingly data-driven society, understanding correlation is no longer a luxury but a necessity. By embracing its power and recognizing its limitations, we can unlock valuable insights and navigate the complexities of our world with greater clarity and confidence.